Welcome to Unit 4. So this is really what the whole course has been leading up to. In this unit, we'll develop an understanding of how modern MOSFETs with channel lengths that are incredibly short by historical standards, just 10 or 20 nanometers long perhaps, will understand how these MOSFETs operate in a very physical but remarkably simple way. We're going to do this by using a description of carrier transport called the Landauer approach. Now, this Landauer approach is a very simple, intuitive, and very physical way to describe electron transport from the ballistic to the diffusive regimes. We'll explain a little more what those terms mean. It was originally developed to understand transport in very small nanostructures, but it's a powerful technique for understanding transport in transistors that are long, medium, or short channel length. Our description of this technique will be very simple and intuitive. I think it's easy to grasp the main concepts and what the approach is all about. But there are many subtle issues that you might find interesting to think about. And I'll refer you to a volume, a set of lecture notes by my colleague Supriyo Datta, for those of you who want to go dive deeper into the physical basis of this approach. So we're going to think about a very small nano device. This is cartoon sketch here is the way we think about it. We've got a device with two contacts. The contacts are very special. Each of these two contacts is going to be in thermal equilibrium with its own Fermi function and Fermi level. So there will be strong inelastic scattering so that electrons exchange energy with phonons, and everything is in thermal equilibrium. There is one Fermi function that describes contact 1. There is a second Fermi function and a second Fermi level that describes contact 2. In general, contacts 1 and 2 could be at different temperatures. Then we would have effects called thermoelectric effects. We're not going to be describing or discussing thermoelectric effects in this course, but those are important effects and the basis for some important technologies. So we have this very small device. The length of the device is L. It is connected, that might be the channel of our MOSFET, and it's connected to two contacts, which will be our source and drain contacts. Our question is, how does the current that flows in contact 1, that'll be in the drain for us, depend on the voltages that we apply to the two contacts? So it's a simple question. The answer is that this expression tells us what current flows. This is an expression that we're going to develop some physical understanding of. Current is equal to some fundamental constants. 2, the 2 represents electron spin. Q is the charge on an electron. H is Planck's constant. So there's some fundamental constants out front. Then there's a parameter that we're going to get familiar with that we call the transmission. This is just a number between 0 and 1. It's the probability that if I inject an electron from the source that it comes out the drain, or vice versa. There's another parameter here we'll call M of E. This parameter is a number of channels in which current can flow. And there is a difference between the two Fermi functions of these two ideal contacts. By ideal, we mean that they're maintained in thermodynamic equilibrium. Electrons can enter and leave them without any kinds of reflections. They're ideal absorbing contacts. You might wonder, how can the contacts be in equilibrium when we have current flowing through this nano device? Well, the assumption is that the contacts are large reservoirs very near thermodynamic equilibrium, so that a small perturbation from equilibrium can drive the current that goes through the MOSFET. Now, we can derive this expression from rigorous transport theory. We can derive it from the Boltzmann transport equation. It's not too difficult to do that, but it's also, I think, intuitively easy to understand, and that's the approach that we are going to take in this unit. So let's just go through some of these terms one by one. Our first question is, what is this transmission all about? How do we understand that? So think about a slab. This might represent the slab of semiconductor. This might be the channel of our MOSFET. And we're injecting a flux of electrons in the left side. And let's begin by first of all saying, assuming that the length of this slab, or the length of the channel, is much shorter than the mean free path, which is the average distance between backscattering events. so that most of the electrons just zip across as though they were in a vacuum, almost. The electrons zip across, they come out the other side. That will be the drain for our MOSFET. And in this ballistic case, where there is no scattering, they'll all come out the other side. We would say that the transmission is 1 in this case. Everything injected from the left comes out the right. Nothing turns around and scatters and comes back out the left side where it was injected. So this is what we call ballistic transport, and we will be interested in what are the IV characteristics of a ballistic MOSFET, because there are field effect transistors right now that operate very close to these ballistic limits. Now the second case is the opposite extreme, and that is a situation in which the length of the slab or the channel of the transistor is many mean free paths long. We refer to this as diffusive transport. In diffusive transport, the injected electrons will undergo some type of random walk as they scatter off of lattice vibrations, impurities, various defects, surface roughness scattering, other effects that can knock electrons in random directions. Some fraction of them will emerge from the right, and that fraction, so the flux that emerges from the right will be transmission times the flux that was injected from the left, and in this case the transmission is going to be less than 1. Far less than 1 if there is a lot of scattering and we're in this diffusive limit. Some of them will turn around and come out the left face where they were injected. So there'll be some fraction 1 minus transmission that will reemerge from the side in which they were injected. So the flux that comes out from the left side and from the right side has to add up to the flux that was injected to begin with, because we're assuming that none of these electrons disappear. There's no electron recombination or trapping, for example. Everything that is injected has to come out one of the two sides. This is the case that we call diffusive transport. The transmission will be a number that is very small compared to 1. It'll all depend on the mean free path for backscattering. Okay, so we can write down a general expression that relates the length of the channel or slab to the mean free path. We can see that both of them are important. When the slab is small, we have ballistic transport. When the slab's thickness is less than a mean free path, much less, we have ballistic transport. When it's much greater, we have diffusive. This is probably the simplest equation that we could write down that would do that, that would give us the proper answer in the two limits. And it's actually an expression that we can derive more rigorously from a simple Boltzmann equation. And in practice, it works quite well under many realistic situations. So we have our diffusive limit, where the the channel length is much larger than the mean free path. The transmission reduces to mean free path divided by channel length, and that's a small number. We have the ballistic limit, where the channel length is much smaller than the mean free path, and the transmission approaches 1. And we correctly described a situation in between, which is where most transistors operate today. I'll just point out that we need to be a little bit careful about definitions of mean free path. Just as though there are several definitions of thermal velocity, and we have to be careful when we're solving problems that we're using the appropriately defined thermal velocity, there are different definitions of mean free path. The most common definition is that the mean free path is just the average distance between scattering events. Velocity times scattering time. I'll denote that mean free path as a capital lambda. The mean free path that we need, we're going to call the mean free path for backscattering. I'll denote it by a small lambda. And they're a little different. So you can appreciate in one dimension why they're different. So let's say I have a nanowire MOSFET, and people are making nanowire MOSFETs. Electrons are free to move only in one direction, say the x direction. And let's say they encounter a scattering potential, which knocks them in a random direction. It could knock them in the forward direction, in which it's as though a scattering event really didn't occur because it just continues on its way, or it could knock it in the reverse direction, in which the carrier backscatters. The backscattering events are very detrimental to the flow of current because they reverse the electron flow. The backscattering events are really the events that we are interested in. And if I assume that this scattering is isotropic, then there's going to be an equal probability of forward and backscattering at each scattering event. The average time between backscattering events then will be 2 times the scattering time. So this mean free path for backscattering would be 2 times velocity times scattering time, or 2 times the conventional mean free path. So I just point that out. We need to be careful when we're solving problems that we use the appropriately defined mean free path for backscattering in 2 dimensions or in 3 dimensions. It involves some averaging over angle when the carrier is deflected in the reverse direction. Those are easy to work out. The volume of lecture notes that I recommended to you by Professor Dada will go through that in more detail. All right, let's now talk about what a channel is. And again, I'll use an idea that my colleague, Professor Dada, likes to use to describe what a channel is. So we'll use this analogy between my university, Purdue University, and Chicago. It's about a 2-hour drive. There is a 2-lane highway that connects us. We would say that there are 2 channels in each direction. If I think of the flow of automobiles as a flow of current, we have 2 lanes or 2 channels in which automobiles can flow to Chicago and 2 lanes in which they can flow back. We would say there are 2 channels for current flow in this case. And that's basically what a channel is, a lane for current flow in a semiconductor. We can be a little more rigorous about this if we think about a band structure. So a channel is basically a state that an electron can reside in, a state that has a velocity. The electron has to be able to move in that state or it won't be able to carry any current flow. So if I have a E versus K diagram like this in 1 dimension, and if I ask, is there a channel at energy E1? Well, I can see that I have a state at energy E1, so there may be a channel there. I also remember that the slope of E versus K is proportional to the velocity of an electron. I have a velocity in the plus x direction, so I have a state with a velocity. I have 1 channel for electron flow in this 1-dimensional band structure. So in general, we can write the number of channels as being proportional to the average velocity in the direction of transport. If I'm in 2D and 3D, I have to average the x-directed velocity over the angles, and then times the density of states in 1D, 2D, or 3D, depending on what I'm working in. The velocity, V of E, is for a parabolic band semiconductor, 1/2 mv squared is equal to kinetic energy. So there's a simple relation between velocity and energy, and then I have to average that over angle properly. And then I'll have some constants out front, h over 4, and the 4 comes from 2 cases you can see intuitively where only half of the states have a velocity in the plus x direction. We're only asking for the channels in the plus x direction. So there's a factor of 2 for that. Normally the density of states includes a factor of 2 for spin. But out front in this Landauer expression, we wrote 2q squared over h. The 2 there was spin. We were already accounting for spin, so that gives me another factor of 2. And that's why I divide by a factor of 4 here. Work through the units here, and you can see that m of E is dimensionless. It is just a number of channels. Okay, so when we teach a beginning semiconductor course, one of the things we like to do is to help students become familiar with the density of states. And we recall that the density of states increases as the square root of energy as I go into the conduction band of a 3D semiconductor. It is independent of energy in the conduction band of a 2D semiconductor, and it goes as 1 over the square root of energy in a 1-dimensional semiconductor. Well, a channel is basically velocity times density of states. Velocity goes as the square root of energy. 1/2 mv squared is equal to energy. So we have to multiply each of these by the square root of energy, and we conclude that the energy dependence of the number of channels in 1D, if I'm in the conduction band, the number of channels is independent of energy. In 2D, it increases as the square root of energy. In 3D, it increases linearly with energy. So density of states and number of channels versus energy are two key quantities in semiconductor physics. Okay, so we've discussed some of the parameters in the Landauer approach, the description of current flow. There is the transmission, which relates the transmission, this number between 0 and 1, to the mean free path and the length of the conductor. There is a number of channels, which tells us how many lanes are there for current to flow in the conduction band or the valence band. And then there is a mean free path for backscattering. And I'm writing it here. These last two expressions that I've written are for two-dimensional electrons, because the inversion layer electrons in a MOSFET will be two-dimensional electrons. The particular averaging over angle in backscattering in 2D gives me a pi over 2. You can see that the mean free path for backscattering is always longer than the mean free path, because some of the scattering events are forward scattering events and don't do much damage to current flow. It's the backscattering events that reverse the direction of the electrons that really cause the reductions of current flow due to scattering. All right, so these are some of the key parameters inside the Landauer approach to current flow. So we have an understanding a little bit, fundamental constants, transmission, number of channels, but we also have an F1, F2. Current does not flow unless the Fermi function of contact 1 is different from the Fermi function of contact 2. It can be different for two reasons. It can be different because their Fermi levels are in different places. And you'll recall that if you apply a positive voltage to contact 2, you pull down the Fermi level in contact 2, and then you have a difference in Fermi levels. The Fermi functions can also be different if there's a difference in temperature. We're not going to discuss differences in temperature in this course. They lead to a different class of transport effects called thermoelectric effects. So the energies over which F1 minus F2 is non-zero, those are the energies over which current can flow. So we integrate over that energy range, and we have all of the current flow. The other energies don't contribute anything to the current. Now, this allows us to understand in a very simple and intuitive way how current flows in this nano device. So let's think of my nano device as a small slab of silicon, large enough that I can still describe it with a band structure like a bulk semiconductor. And that's frequently a good approximation until you get to exceptionally small transistors. So we have an E of k that's parabolic with some effective mass. We have a Fermi function in contact 1. We have a Fermi function in contact 2 that I'm showing as lower because I'm assuming that I'm applying a positive voltage in contact 2, and we've pulled that Fermi level in contact 2 down. Okay. Now, if I look at the energies below the Fermi level of contact 2, and just for simplicity, I'm going to think about this happening at t equals 0, because it makes it a little easier to see what's happening. All of the states below the Fermi level want to be filled. All of the states above want to be empty. So if I'm below both Fermi levels, then all of those states are filled from F1, and they're filled according to F2. So F1 is equal to F2 is equal to 1. Those states are filled. F1 minus F2 is 0. These states will contribute nothing to the flow of current. It's only states in this Fermi window that will contribute to the current flow. So we can understand what happens. These states have a positive velocity. They have a positive slope on the E of k. They have a positive k. They'll have a positive velocity. They want to flow from left to the right. Any electron that comes into this state, and let's think it's most simply to think about the ballistic case for now. Any electron that comes in from that state had to enter from contact 1, because contact 1 will inject them with positive velocities. Well, contact 1 looks at that state. Let's say that state is empty. Contact 1 looks at that state and says, that state is below my Fermi level. It should be filled. So contact 1 sends an electron in and fills that state up. Okay. Now contact 2 looks at that state, and contact 2 says, that state should be empty because it's above my Fermi level. So then the electron will flow out into contact 2. And that's sort of the way current flows in these small nanostructures. An electron comes in from contact 1 to fill up the state in the Fermi window. Then an electron flows out from that state into contact 2 to make contact 2 happy. The state should be empty. And that results in a current flow that is in the opposite direction or in contact 2. So that's a very simple way that we can think about how does current flow in these small nanostructures. All right, so hopefully you've gotten a little bit comfortable with this expression that we're going to use. We will use this expression to understand current in small MOSFETs, and we'll also see that it can equally well be generalized, and we can understand current in long channel MOSFETs just as well with this expression. So this is the Landauer expression, and we will see how to apply this expression to the linear and saturation regions of MOSFETs. Now the next topic then, we know that the linear region is when we have a low bias between the two contacts. So we will have to discuss how we simplify the Landauer expression when there is a low voltage difference between the two contacts. The second case we would like to do is understand the saturation current when we apply a high bias between the two contacts, and we'll discuss in the next lecture also how to simplify the Landauer expression when we apply a high voltage between the two contacts.